And our next presenter is Ivan Kovalets. He is the head of environmental informatics departments at the Institute of Mathematical Machines and System Problems of the Ukraine National Academy of Science. Dr. Kovalets will present the structure of meteorological wind resuspension and atmospheric transport model that could be used for assessment and forecasting of secondary air pollution assessment resulting from wind lift of contaminated dust. The presented model chain is integrated in a web system that was used in April 2020 for assessment of radioactive air pollution resulting from dust storm and wildfires in the area of Chernobyl Exclusion Zone. Dr. Kovalets considers that the developed modeling tool could be potentially used for the assessment of air pollution created by resuspended dust from the drain plant of Kakhovka reservoir. And other similar applications are also possible. So I'm passing to Dr. Kovalets.
Thank you. Thank you for also organizers for this possibility to present our results. First, I will say a few words about our team. Do you hear me okay?
Yes, I can hear you well, and I see the slides.
Next slide, please. We represent Institute of Mathematical Machines and Systems, which is one of the parts of the Cybernetics Center. In the 1986, following Chernobyl incident, the headquarters for forecasting of radionuclide water contamination was organized in this institute because by that time, this was the only place in Kiev where there was such a large screen where they could show online maps with contamination based on, and this screen was based on the control center of Soviet space flight program. That's why the Division of Environmental Forecasting was organized in the Cybernetics Center, and physicists, environmentalists, chemists, fluid dynamists from several institutes of Academy of Sciences were welcome, were invited. Next slide, please. So the first team leader was Dr. Mark Zhelezniak, who is now professor of environmental radioactivity in University of Fukushima. And following, since that time, this division consists of 3 departments. One represented by me is environmental informatics and meteorology, meteorological modeling is considered in this department. Other is my teacher, Professor Vladimir Maderich, who is oceanographer, well-known oceanographer, and he leads marine system modeling department. And one more department is general environmental modeling, who is head by a corresponding member of Academy of Sciences of Ukraine, Dr. Igor Brovchenko, who is also pupil of Vladimir Maderich. And also we have a spin-off company of our institute. It's called Ukrainian Center of Environmental and Water Projects. Next slide, please. On the next slide, we see several applications of our department. It includes assessment and calculations of the dam that was built on the Pripyat, on the bank of Chernobyl cooling water pond. Also applications for assessments in building new safe confinement of Chernobyl nuclear power plant. In particular, it was my work to estimate consequences of potential break or demolition of the new safe confinement by tornado And since approximately 1993, we are permanently involved in the creation, development, and of the European Nuclear Emergency Response System, RODOS. It is like Windows. It is permanently developed. New modules appear there, redesigned, and so on. It was successfully applied during Fukushima. And now it is implemented in Ukraine in approximately 6 ministries, including Ministry of Environment, Ministry of Emergency Service, Ukrainian Hydrometeorological Center, Chernobyl Zone, and so on. Next slide, please. So motivation for this presentation. We know that contamination of land, and in particular drying the bottom of Kakhovka reservoir, could lead to large source of air pollution by mechanism of wind lift, or it is called also wind resuspension. In fact, in Ukraine, we have a long history with Chernobyl Exclusion Zone, which had become the permanent source of secondary air pollution by wildfires. That is another mechanism for secondary pollution, resuspension by fires. Both mechanisms are considered in our developments, mainly in connection to studies of Chernobyl Exclusion Zone. And here on the slide, we see a screenshot of article in Rubrika, Czech paper, where they measured toxic compounds on the bottom of Kakhovka reservoir to study potential of this source of secondary air pollution. Next slide, please. So briefly, I will describe the existing in our department chain of meteorological and atmospheric transport models, parameterization of wind resuspension. We'll describe application in environmental safety assessment project regarding remediation of radioactively contaminated territories, and application for assessment of air pollution from wildfires and dust storm in April 2020. Next slide, please. So for meteorological modeling, we use WRF meteorological model. I think we were the first in Ukraine who set up this model, and some operational weather forecast sites which you use this model based on our developments. The high resolution meteorological fields that could be produced by this model with 10-kilometer resolution are highly beneficial for improvement of atmospheric transport calculations. The boundary and the initial conditions for this model are global meteorological fields calculated on coarser grids like 0.5 degrees or 0.25. So the operational system developed, which uses this model, developed in our department, now operates in Ukrainian Hydrometeorological Service as part of supply of RODOS Ukraine system with meteorological data, and also as part of flood forecasting system for Ukrainian Carpathians. Next slide, please. So here we see several steps involved by meteorological forecasting. It includes operational download of global data, preparation of topography, soil cover, and land cover and soil geographical data. Also data assimilation could be included, and output numerical weather prediction fields are thus calculated. Next slide, please. Here is operational configuration of computational grids used in Ukrainian Hydrometeorological Center. There are outer domain with 0.15 degrees resolution and inner domain with 0.05 degrees resolution, which approximately corresponds to 4 or 5 kilometers. Actually, there is also the third domain that covers the part of Carpathian region, the Prut River Basin, Prut and Siret River Basin with 1 kilometer grid resolution for flood forecasting. Next slide, please. Here is we see evaluation of meteorological forecasting against data of automatic weather station at Rivne nuclear power plant. It is very good station that measures with good accuracy 10-minute averaged wind speed and wind direction, and it also has measurements important for atmospheric transport calculations such as net radiation and others. So the basic statistical parameters of error, mean absolute error and mean of wind direction and wind speed are correspond to state-of-art weather forecast models published elsewhere in the world. Next slide, please. Here is comparison of upper level wind speed and wind direction against SODAR data, vertical wind profiles collected also at Rivne nuclear power plant. I can surely state that this is the only in Ukraine study in which the upper level fields in the bottom 1-2 kilometer boundary layer of atmosphere were compared with measurements by the simple only reason that there are no vertical profiles measured in Ukraine. Presently, radio zones, first of all, are not launched. Secondly, radio zones start measurements from approximately 700 meters. And there are no other measurements in Ukraine in the bottom kilometer except SODAR of 2 nuclear power plants, one of which is Zaporizhzhia. So the only nuclear power plant that could measure wind distribution in the lower kilometer is Rivne. Next slide, please. Regarding atmospheric transport, we have several options. One option, the most common, is atmospheric dispersion module of the Rhodos system, for which our team is co-developer. Personally, me, I was postdoc in National Center of Scientific Research Democritus, Greece, which is the key developer of this atmospheric dispersion module. So we are co-developers of its models. And also we use, depending on the purpose of study, very known models like Gaussian PAF model CalPAF, which was previously EPA recommended model. Also Lagrangian particle model FlexPart, which is used by United Nations CTBTO. Who is interested those could see what means this abbreviation organization. And we also use computational fluid dynamics models for studies in the urban abstracted areas. Next slide, please. So briefly about models, Gaussian PAFs consider the continuous release sequence of instantaneous releases, so-called PAFs, in which in each path the matter is distributed according to Gaussian instantaneous release formula, and all paths contribute to concentration in given point. This approach is old and very computationally efficient, but when paths grow, they clearly they can become 1-2 kilometers, and they of course don't represent actual distribution of matter in instantaneous release. Next slide, please. The most state-of-art models are Lagrangian particles models, in which release is represented as sequence of particles which move by average wind and also stochastically move by wind fluctuation. All this describes average transport and turbulent transport. The only problem for this is high computational demand. Next slide, please. Besides atmospheric turbulence and mean wind, models describe washout of pollutants by rain, dry deposition by friction, also plume rise when initial release is hot, and so on. Next slide, please. Regarding parameterization of resuspension, the basics for this parameterization is the old known Bagnold formula, in which flux of particles, aerosols, from the land is proportional to the so-called friction velocity. Friction velocity is characterizes friction imposed by moving air on land, and it is roughly proportional to simple velocity by known formulas. The problem is with these parameters A and N, because different literature studies have very different assessment, and the difference by 2 orders of magnitude in assessment of wind resuspension is not impossible in different studies. Next slide, please. Nevertheless, we implemented in our model chain this resuspension parameterization because we were involved in the project on development of remediation strategy of the former uranium production facility, Pridneprovsky chemical plant in Ukraine. It is in Kamensk, close to battlefield. Who don't know, this is the largest uranium production for military uranium in Soviet Union. So it contains large deposits of the products of uranium production. It's mainly radium and also uranium. It was closed without all proper decommissioning procedures in the beginning of Soviet Union. It was simply, how to say, thrown off. People went out without any procedures. So some tailings were lost because they were land was over tailings, and they were lost. People forget where tailings are. For instance, there is hospital in which garden there was found tailing. It's called lazo, tailing lazo, of this Kamensk Pridneprovsky chemical plant. So in the beginning of 2000s, that was realized great concern about this territory, and here are some objects of this territory. So we see Kamensk city. We see largest tailing, Sukhachivsky tailing and base C. We have an industrial site with tailings, and all these settlements are there. When a project on remediation started and program on remediation started, the situation was as we described, as I described. So there was a need to assess what kind of doses could be received by people, for instance, in Taramske settlement or in Svitoe settlement by wind resuspension from Sukhachivsky tailing. We see this Sukhachivsky tailing in the photograph, where radium is not covered. It is simply grass over it. Next slide, please. Next, not previous. So we were invited to people who worked there with monitoring, who collected data on soil contamination with radionuclides. And we integrated this data in models to evaluate yearly average and maximum possible concentrations of radium in air. Next slide, please. So here we see comparison of our model results with measurements of air contamination in above Sukhachevsky tailing. We see that on average we see good results. Maximums sometimes are larger than in observations, though because of very unhomogeneous distribution of land contamination, even within one tailing, it is very difficult to capture all details of the air contamination in the vicinity of tailings. Next slide, please. So the model was considered. All this was done with the help of international aid programs like SIDA, Swedish program for help for other countries, and national programs. And also recently it was European programs of INST program. Here we see, so finally we obtain a distribution of maximum concentration through 5-year periods that could be received depending on distance and direction in settlements. And these maps were then used for assessment of health effects and for assessments of what kind of remediation strategies are the most justified for these tailings. Next slide, please. Some results also regarding this is published in Journal of Environmental Radioactivity, so who is interested could find this study. Since that time, we were convinced that resuspension is adequately described by our approaches and our models. So we decided to integrate this in separate system for calculation of operational calculation of secondary air contamination due to wind resuspension, mainly because Chernobyl Exclusion Zone is also important, could be important source of secondary contamination. Next slide, please. So here we just to see interface of this system, we define computational domain, we define what radionuclides. It was primarily for radionuclides, but also, of course, other contaminants in soil could be included. Next slide, please. So here now I will describe some experience of use of this system for studies of air pollution resulting from wildfires and dust storm in April 2020 in Chernobyl Exclusion Zone. Next slide, please. So as you probably know, the largest in the history wildfire in Chernobyl Exclusion Zone happened in April 2020. The territory, actually more than 30,000 hectares in Chernobyl Exclusion Zone was covered by fires. And the most contaminated part of the territory, like red forest, were also burned. It started on 3rd of April. Their intermediate pause in these wildfires was 13th of April, when rain temporarily shut down wildfires. But on the 16th of April, extremely high wind, next slide, please. High winds lead to dust storm in all northern Ukraine, including Chernobyl Exclusion Zone. By assessment of State Emergency Service, it was the first dust storm in this region in a few last decades. If we consider that wildfires were also the largest in the 30 years, we see two extremes: dust storm, which happen once per approximately 30-50 years, and wildfires that happen one. We see compound extreme, two extreme events that each of which happens approximately once per several decades. So on 16th, 17th April, they happened together. Next slide, please. Here is measurements of particular matter in Kiev in April 2020, and during these days, from 16th to 19th of April, we see extremely high levels of particular matter. If, for instance, there was also during earlier days, the levels were sometimes quite high because of wildfires. But these extremely high levels were due to combination of wildfires with dust storm. Next slide, please. So for simulation, first we simulated, tried to make separate assessment of contribution from wildfires and dust storm. To calculate contamination created only by wind lift, we take map of cesium-137 fallout following Chernobyl disaster and performed assessment of resuspension and simulation of transport for during dust storm period. Next slide, please. Here is map of land contamination following Chernobyl. Actually, it is not measurement, it is reconstruction by calculations, but we compared it with measurements that it closely follows measurements, because we have also wind atlas of radioactive contamination of Ukraine. Unfortunately, it is not available for us in digitized forms, but with what we compared, we have good coincidence. Next slide, please. And here is a map of calculated by the system average concentration in air for the dust storm period. If we look on values, we see that maximum values are up to 5 millibecquerels per cubic meter, which is could be compared with background values, which is a few 5 millibecquerels means 5,000 microbecquerels, compared to background a few microbecquerels. For instance, in Kiev, background is 5-6 microbecquerels. Next slide, please. Here is some comparison of this simulated concentration created by dust storm only, and with background concentration at different locations, including Chernobyl Exclusion Zone, Slavuty, Chernihiv, so settlements close to Chernobyl zone, but as far as Kharkiv and Sumy. We see that even in Kharkiv, where the background concentration of cesium in air is about 2 microbecquerels, we have 13 microbecquerels created by dust storm. Rivne, which is also far, we have 10 times more concentration created by dust storm as compared to background. This effect of dust storm could be well captured by measurements. It could be essential even far from Chernobyl zone. Of course, all these values, just to make it clear, are far from from permissible health limits. So they are far below, but they are essentially more than background. And this background, to be clear, is not natural background. It is Chernobyl background. There is no natural cesium-137 in air, no at all. All cesium-137 in observed and considered as background in Ukraine comes from Chernobyl deposition. Next slide, please. At the next step, we combined modeling of wildfires contribution and secondary contamination from wind resuspension. It is, by the way, interesting to mention that parameterization of wildfire emission is based on the empirical fact that if you burn all vegetation at certain territory of Chernobyl zone, from 1 to 5% of total inventory of radionuclides at this zone is emitted in air. So this is basics for, which lies in modeling of radionuclides modeling following wildfires by everybody. So this so-called resuspension factor. So we can pose questions that if we will in future have to evaluate some other contaminants, how they come in air following wildfires at contaminated territories, we will have to assess this resuspension factor. But just to know that for Chernobyl zone, for cesium, it is from 1 to 5% of total inventory that comes in air after burning all vegetation in this territory. It's based on field studies, experimental field studies. Next slide, please. So we have figure is a bit. It was white, but it became black. So here we have a map of time-integrated concentration of cesium simulated and locations of monitoring stations, which data were used for improvement of assessment of emission inventory. So actually data all over Europe and Ukraine were used in this study. All these stations detected radionuclides from wildfires. So all these stations represent locations where background was increased by several times because of Chernobyl wildfires. Next slide, please. So here we see first guess estimates, which are not based on comparison with measurements, but based on these resuspension factors, and emissions estimated, first guess estimated emissions, and adjusted estimated emissions by minimizing difference of model with measurements by solving inverse problem. Separately, with separately divided sources from resuspension and from wildfire. As we can see from this figure, the source from resuspension estimated in this study is about 20-30 gigabecquerels during 2 days, which is by the factor of about 5 less than source due to wildfires. So quite quickly, despite wildfires were shut down on April 13-15, quite quickly strong wind made them again active, and wildfires contributed more than wind resuspension. Next slide, please. Here we see several times with simulated concentration field during 16th of April when dust storm started. We see that we don't see here because of this black background, but Kiev is on the boundary of this plume. That's why sometimes radionuclides from Chernobyl zone reached Kiev and sometimes not, during one day. Next slide, please. And on this figure, we see separate simulation of all sources contributing to contamination and only dust storm. We see that figures are close, despite the storm is much less than wildfires. Why? Because wildfires is elevated source from ground to a few kilometers. And this emission is distributed in about lower 5 kilometers of atmosphere. And despite source from wind resuspension is by several times less than source from wildfire, it happens near ground. So actually it contributes major of detected emission during these days. All this is published in atmospheric environment paper, not 2020, but 2022. Next slide, please. But DOI link is correct. And now finally we see a comparison of the first figure that shows particular matter in Kiev with measurements of cesium in Kiev and with simulation of cesium in Kiev for the April 2020. We see that in contrast to measurements of particular matter, on which the measurements during dust storm 16th, 17th of April were much more than, for instance, measurements on 10th of April. The cesium during dust storm was less than cesium on 10th of April. This shows that majority of this particular matter detected in Kiev came not from Chernobyl zone, but from other areas affected by the storm. While on 10th of April, this wind was from Chernobyl zone to Kiev, and it was heavily affected by radionuclides from Chernobyl zone. Next slide, please. So in conclusion, I must say that we developed model chain of weather forecast, wind resuspension, atmospheric transport model. It is applicable for scenarios of secondary air pollution following wind lift or resuspension of contaminated dust. Also, it is possible to consider combined scenarios of dust storms and wildfires. We demonstrated application for environmental safety assessment of the radioactively contaminated territory and for analysis of scenario of compound extreme when wildfires in Chernobyl zone were combined with dust storm. Finally, thank you for attention.
Thank you very much, Dr. Kovalets, for this very intense presentation. Are there any questions? I see no in a spreadsheet. If someone would like to ask with microphone, please unmute yourself and ask your question. Okay, while I see no questions, you mentioned, at least in the text which you sent to us, to organizers, that your model can be used for predicting particulate or dust distribution from the bottom of Kakhovka reservoir. And how far are you in this work? Can it be, for example, predicted how far this contamination can migrate, to what radius or to what distance?
Yes, we can apply our models for this work, but presently we don't have collaboration regarding measurements. We have to have measurements of contamination in bottom and also other information about state of bottom, for instance, its water content and so on. So it requires collaboration with monitoring people.
Then this, okay, are there any questions? Maybe someone came with questions. Irina?
Yeah, thank you, but I'm sorry, I will ask in Ukrainian. В мене запитання таке, пане Іване, скажіть, будь ласка, ви працюєте з даними в якомусь, як в реальному часі? Ну, є якісь механізми цієї повідомлення населення, чи це не з вами пов'язано, чи з вами? Можливо, це не скільки до доповіді, але просто цікаво, тому що це важливі дані про забруднення повітря, це те, від чого залежить життя людей.
Ну, наразі от система RODOS, ми її супроводжуємо в усіх відомствах, відповідальних за саме таке інформування. Тобто, наприклад, в Українському гідрометцентрі є створений Центр прогнозування наслідків радіаційних аварій. Це ПНРА. Ми вже більше 5 років постійно супроводжуємо там цю систему, консультуємо їх, робимо так, щоб... А там оперативний штаб, це оперативна структура, вони мають це повідомляти. Те саме в Державній інспекції ядерного регулювання. Ми супроводжуємо цю систему, ми їх консультуємо, супроводжуємо, допомагаємо їх рахувати, але вони, більше того, неодноразово вони про нас згадували в своїх офіційних повідомленнях, у тих випадках, коли їм треба було для офіційних повідомлень нашу пряму безпосередню допомогу. Ну, наприклад, у жовтні 2017 року, коли був зафіксований рутеній, фактично вони опублікували наш звіт як свою офіційну позицію – Державна інспекція ядерного регулювання. Тобто дві основних структури щодо радіаційних, принаймні, аварій – це Державна інспекція ядерного регулювання, і у неї є ще інститут ГІП, який підкорений до НТЦ ЯРБ, Державний науково-технічний центр ядерної радіаційної безпеки. І Український гідрометцентр, там у них спеціально створений центр. Це все, грубо кажучи, це все ми.
Дякую дуже.